To today's Thinking About lecture presented by Dr. Mark Reed, who we're delighted to have with us. Mark is a senior lecturer at the University of Birmingham, a researcher in computational solid state chemistry, and also the Royal Society of Chemistry SIAS coordinator. I also found out today that Mark is a member of the Birmingham Centre for Nuclear Education and Research. So additionally, if anybody's got any questions about that, I'm sure he'd be willing to answer them. Okay, so we've also got our two student panelists with us, Tassin Syed and Cameron Brown, both from Dulwich College, both in year 12 and both studying chemistry A-level, which is brilliant. So I will pass over to Dr. Reed now, and I hope you enjoy the lecture on infrared spectroscopy. Thanks.
Well, thank you very much for that introduction, and welcome. Can I just check everyone should be able to see my screen of my presentation? So normally around this time of year, we visit schools giving this hands-on spectroscopy in a suitcase workshop where it links in with the A-level syllabus. A-level year 12 and year 13 students actually get the chance to run their own infrared spectra. Because of the current situation, obviously we can't do this, but we've got the next best thing. I'm going to go through the types of things that a workshop will involve. I've also got some videos and some pictures of actually using the equipment as well. So we'll be able to see this. So first of all, I begin the talk with either a refresher or an introduction to infrared spectroscopy. So whether you're year 12 or you're 13, hopefully you'll take a little bit away from it. So to begin with, I'm sure you're all very familiar with the electromagnetic spectrum, and we know there's a relationship between the energy of the radiation and the wavelength. The longer the wavelength, like radio waves, long wavelength, low energy, as the wavelength decreases, we approach X-rays and gamma rays, which have a high energy intensity. Now, we're all very familiar with a part of that spectrum called the visible region, because our eyes can detect that, and that's how we perceive colors. We can't see either side of that region, but if we could see lower in energy, neighboring that region is the infrared region. Now, like visible, it is a region. There are several wavelengths within that region. Although we can't see them, they're very useful. Infrared is used for remote controls and also for thermal imaging, because hot bodies emit infrared radiation. And if you detect that and convert it to color, as the hot cup of coffee at the bottom shows, you can visualize this infrared radiation. It's very important for chemists because it just so happens that the energy associated with that wavelength is also the energy required to vibrate a chemical bond, to vibrate the two atoms that bonded together. So that's the link with infrared in chemistry. We're also very familiar with the microwave region. We put our food in the microwave, irradiate it. There's an interaction between the microwave radiation, the water molecules in our food, and through rotation and friction, that heats our food up. Now, that interaction of radiation with our matter is simply the definition of spectroscopy. All spectroscopy is the study of how that radiation interacts with a sample and how we get some chemical information from that. So that is infrared spectroscopy in a nutshell, and the electromagnetic spectrum. Now, a lot of these resources I'll make available afterwards.
Dr.
And there's a
Reed,
worksheet. Sorry,
can I interrupt you a moment? At the moment, we're seeing sort of all your slides. Are you able to share your screen so we can see it bigger, the main slide?
Oh, sorry, yes. Is that better?
That's perfect. Thank you very much.
Thank you. Thank you for letting me know. Do apologise, everyone. I was obviously sharing the wrong screen there. So we had a quick look at the electromagnetic spectrum. We looked at where infrared was. But chemists actually use quite a bit of that spectrum for different techniques, because it's very rare in chemistry that one technique will give you all the answers. In fact, usually we rely on several. And in this workshop, we're going to look at infrared and also mass spec and putting the two bits of information together to work out an unidentified compound. These are techniques that you'll cover both in year 12 and year 13, and this useful table links them to the part of the electromagnetic spectrum that they use. For example, NMR, nuclear magnetic resonance, or if you go to hospital, they call it an MRI scan. That uses radio waves, and you'll learn more about NMR in year 13. We're going to focus on infrared spectroscopy today, but you'll also remember UV visible. You may remember flame test that you used and how the transition elements in the flame gave off different colors. Lithium, for example, giving a bright red, boron green, for example. That's an example of visible spectroscopy. So very useful to link those with part of the spectrum that we're using. And by the time we get up to X-rays, the wavelength is so small that they're actually diffracted or bent by the very small distances between ions in the crystal. They produce a pattern, you interpret that pattern, and that's where you can work out the structure of crystals. So that's how DNA, for example, had its structure elucidated, and we still use it today for important ceramics to work out the structure. Everything from semiconductors, electrolytes, new battery materials, very useful techniques. Part of this suite of techniques includes mass spectrometry. Slightly different from the others in that the molecule is actually broken apart or bombarded. All of the others are called non-destructive techniques, where we get some information, we don't destroy the sample. And that, of course, is very useful for forensics, where we only have a very small amount of sample. We wish to know what it is, but we don't want to destroy it, so that we can either use further tests or use it for evidence. So this is an overview of techniques. We're now going to focus on infrared. So what do we need to produce an infrared spectrum? Well, we need an infrared spectrometer. We need a source of infrared, and I'll come to that with an instrument shortly. And we obviously need some way of holding our sample. Infrared spectroscopy is a very versatile technique because we can analyze gaseous, liquid, or solid samples as well, just by changing the sample head. Now, we're only going to look at liquids and solids today, because to analyze gases, I'll have to reconfigure the instrument. Now, some teachers may remember the older instruments where we needed to do some sample preparation. The sample was placed between two potassium bromide discs and placed into the instrument. If you were trying to analyze a solid, you would use a small pestle and mortar, grind that up with some Nugel and oil to make a mull. And it was quite time consuming, and there was a lot of expertise in getting the right sample preparation. With this instrument, and with a lot of modern instruments, there is no need for sample preparation. You place the sample directly onto your sample head, as we shall see. So once the sample is on there, the infrared produced by the instrument passes through a sample and then is analysed by a detector to see how much has passed through. And our result, our infraspectrum, is shown here. Essentially, it's a graph of results. And along the x-axis, we have the infrared region, the wavelength, although we use units of wave number, which is simply 1 over the wavelength. So that represents the infrared region. And on the y-axis, we have transmittance, or what percentage of the infrared produced has passed through our sample and arrived at the detector. When that's at 100%, everything has passed through that was produced at wavelength, nothing's been absorbed, so very boring, nothing's happened. But you can see in this spectrum, there are certain peaks where the infrared has been absorbed by a certain bond. Remember I said the energy matches the vibration of the two atoms. When that happens, we see a peak in our spectra. When we see a peak, we know that the energy has been absorbed. We can then look up the energy, match it to a bond energy, so we know that that bond must exist in our sample. That's really the foundation of infrared spectroscopy. So in this particular example here, we can see we have a ethanoic acid, and that very sharp peak at about 1700 wave number is caused by infrared being absorbed by the carbonyl group, carbon double bond oxygen, and the broad peak around 3300 is the OH group for the from the molecule as well. So the first stage is to run a sample, identify the peaks, look those peaks up in a lookup table, and that will tell you what bonds must be present in your molecule. Once you know what bonds are present, you then have to, like a piece of a jigsaw puzzle, put those together in order to then work out, well, how is my molecule arranged? So when you look at the infraspectra, we typically look at peaks that are above about 1500 wave number, because here we have clearly defined and uniquely assignable peaks, and you look them up in the lookup table. However, you can see the purple region on this diagram below 1500. Usually it's a little more complex. Some of the peaks coalesce, they merge into each other, and they're usually a more complicated pattern. Several of those peaks may be the lookup table, but in general, we can't identify those. And you'll see why later when we look at some vibrational modes of these molecules. So this area is called the fingerprint region. And for A-level interpretation, we don't normally go into this region. There are some peaks though that are on the cusp. So for example, a carbon single bond oxygen is around 12 or 1300 wave number. That's it's a grey area in between. But in general, we avoid this area and just look to identify the key peaks. However, it has come up in the A-level previously, what may this region be used for? And the answer is, although you can't get any uniquely identifiable peaks, the pattern, if you compare that pattern with, say, a database or an online library, you can pattern match to identify your molecule. And we'll actually be doing this with an online database later. So for the purposes of the A-level syllabus, we avoid this region, but in practice and in forensics, this region is actually quite useful, and it has a lot of detail that the computer can use in a database to pattern match. So once we have our spectrum, we've identified our peaks, we've used a lookup table, we can then work out, well, what must our molecule contain? And also remember that if you don't see a peak, that's also useful information, because it tells you what bonds can't be present in your molecule. So if you've got some other information, say from mass spec, you think there's an alcohol involved, but if you don't see the OH peak, then it can't be an alcohol. That oxygen and hydrogen have got to be bonded by some other way. In this series of samples, if you have a carbonyl stretch and an alcohol, then of course it means that the molecule contains both of those groups. So you could have an aldehyde or a ketone or indeed an ester. You then have to piece together, a bit like a detective, what else is there. And also, if you have both the OH group and the carbonyl, then carboxylic acid is a candidate, as we saw previously. So the instrument that we're going to be looking at today is a portable FTIR, Fourier transform infrared. The workshop that's usually delivered is called Spectroscopy in a Suitcase, and its name derives from the fact that this can be carried around in a suitcase. It is very portable, and it's about the size of a shoebox, whereas a few years ago, I'm only going back about 5 or 10 years, these things were about the size of a bench. They would stay in a laboratory, they would require a technician to run them, and they certainly weren't portable. So the fact that just like mobile phones, that technology, advances in optics and electronics have enabled us to make this smaller, it's now portable. So you can take it to a factory, to a forensic scene, for example. So it's a very useful piece of kit, and the workshop actually brings this instrument to the classroom, so people get to actually use it to get their spectrum. So this is the Infra-Red Spectrometer that we're going to be using. Part of the workshop, as I mentioned, also looks at some other data to use. And I am going to make available the handout that we use. But part of the other data that commonly used for compound identification is mass spectrometry as well. Now, I'm not going to go into the theory too much here. It also depends on the syllabus. I think some exam boards do the deflection of the ions through a magnetic field, and some do the more modern technique of time of flight. Either way, you're bombarding your molecule with electrons. The first thing that happens is that you displace an electron, give that molecule a charge. If nothing else happens, that molecule will rise to the detector. That is your molecular ion. So when we come to identify, the heaviest peak, the largest peak you see is your molecular ion, and that gives you the molecular ion mass. But further electrons may break the fragile parts, that molecule apart. The mass spec simply orders those fragments in order of their mass, or more correctly, their mass to charge ratio. I'll come on to how we use that data later, but mass spec is another important technique. So I want to make available the PDFs. When you look at that, this is the booklet that's given to students, and the first part covers a general introduction to spectroscopy. We then focus on infrared, and it actually gives you the lookup tables that you can use to identify peaks that you observe as to what bonds must be present in your molecule. A little introduction to mass spec and how to interpret the mass spectra, and there's a similar table like the infrared lookup that gives you some common stable fragments and their mass number as well, so you can look up what parts are in your molecule. And the exercise that the student perform is to take all this data, put together the empirical formula that's given. As you can see here, the empirical formula, the information from the mass spec, and the infrared that they run themselves. Put all that information together, and you've got enough to identify your unknown compound of interest. Now, with the mass spec, the largest peak is your molecular ion, as I mentioned, and you can look up the mass spec of the other peaks that are observed. But also, if you take the difference between your molecular ion and the subsequent peaks, that mass difference gives you the mass of the bit that's broken off. So that's also useful in working out how your molecule is composed. And as I mentioned, there are a couple of lookup tables we use. For the infrared, you will observe where your peaks are on the spectrum. That tells you what chemical bond must be present, and it gives you examples of functional groups that could possibly be there. But you need to look for other evidence. For example, for an ester, as well as having a carbonyl, you would also expect to see the carbon single bond option peak as well. So that is an overview of the two techniques. Once you have this information, it really is like a jigsaw puzzle. You have to put all this information together so that it kind of makes chemical sense. And this is one of the key challenges of the A-level, because up until now, you've probably gone through a set procedure, and if you followed it step by step and done everything in the right order, you get the right result. With compound identification, it really is a little bit of trial and error. You quite often don't get the right answer first time. Sometimes it might fit the mass spec data, but then you have to go back if something doesn't agree with the infrared. So you have to look at all of this data and be a little bit iterative, try and piece it all together. But I'm going to show you with running some samples how this happens. So before you show the instrument, I'm going to first of all share the screen of the laptop that controls the instrument, because it's important for you to see how this instrument works. First thing we have to do is a background correction. So when I look at my screen, this is the laptop screen. I've clicked on measure my background. And at the green bar at the bottom, you can see it does several scans. Now, I've only set it to 8, but that's sufficient for a quick turnaround. And after 8 scans, it's already measured the air above the instrument. That is our background atmospheric correction factor. I'm now ready to run some samples. So if we look at the instrument, here is the infrared spectrometer. As I say, about the size of a shoebox. I'm now going to analyze sample B. You can see I'm taking the lid off it. This is liquid. I'm using an ordinary glass pipette, keeping it vertical, drawing some liquid up, and placing it on that sample stage. You can see a metal disc. I'll zoom in shortly. In the center of that metal disc is a very small FTIR diamond, and it's on that diamond we place a few drops of sample. So you can see as we zoom in just what a small amount of sample we actually use. You can see the diamond crystal right in the center, and we're just going to place a few drops on top, and that is sufficient to give us a spectrum. Now, this is important in forensics because quite often you don't have a lot of material to analyze. So if you've got a very sensitive technique like infrared, we can only use a few drops, and that's enough to give us some information, as you'll see. I've done this in Big N because although I made it look quite easy, we've got a long glass pipette, sometimes it shakes, pupils sometimes shake a bit. So this is another way to stabilize that pipette using your other hand as well. So once our sample is on that instrument, we go back to the laptop that controls it, and we now run our sample. So I'm going to go from the instrument back to our control, run our sample, and you'll see how quick. This is real time. I'm labeling the sample, sample B. I'm now going to start my sample measurement. Down here, you'll see it's doing the 8 scans. And after the 8th scan, it will average that data to remove any noise. It will take away our background. And then just what I've been talking, that is the spectrum. That is the infrared spectrum of sample B. All I'm doing now is putting some figures to those peaks so I can look them up in my lookup table. And then I print the spectra so that we can then have a look at it and analyze it further. So in the classroom, this is printed out. And I am going to come back to these PDFs because we save that spectra and that is what is produced. So you can see in just a few seconds, with a very small amount of sample, I've got an infrared spectrum, which is very useful. And then in the classroom, what we do is print it out. So we've got a hard copy as well. And this is very useful because you can annotate their spectrum. And if you want to compare spectra, you can put 2 against each other, hold them up to light, and see which peaks are there, etc. So that, in a nutshell, is how we run a sample. I'm now going to have a little look at what causes those peaks. So what is it that's absorbing that infrared? Now, as Dr. McQuain kindly mentioned, I'm a computational chemist, so I'm going to show some molecular modeling studies. And this is what's happening to a molecule when it absorbs that infrared at the right energy. So we can see a very simple molecule of water. There's a particular energy, a particular wave number of infrared that causes this bending motion. You can see the hydrogens, the angle between the hydrogen, the oxygen, and the hydrogen is varying with time. This obviously slowed down, exaggerated. This is what's happening to a molecule. So at this stage, we're not altering the bond length, but we're altering the angle. There is another slightly different wavelength which causes the stretching mode. And in here, both of the hydrogens are moving away at the same time. So that is a symmetric stretch. And as the name implies, you can also get an asymmetric stretch as well, where they are out of phase. So all of these take slightly different wavelengths of energy, so the peak will shift slightly. If we come to a molecule, and this actually is an ethanol molecule, so sample B, and one of the spectral modes is called a wagging mode. You can see the OH group on top here. The hydrogen is just moving backwards and forwards. It's not altering the bond length. That's called a wagging mode. But the key peak that you identified around 3,300 is the OH stretch. This is a classic OH stretch. And what's causing that peak is the oxygen and the hydrogen bond absorbing that energy vibrating. So why or what is that a function of? Well, the energy required to vibrate the bond is a function of the strength of the bond, whether it's a single, double, or even a triple bond, and also the mass of the 2 atoms between them. That is why the molecule with different atoms or different bonds, we're going to get different energies, hence different peaks, since we can then identify the different bonds from the spectrum. It's also important to note that in this example, only the OH group is absorbing this energy. This is one particular wavelength that only matches the vibrational mode of the OH. You can see the CO, the CH aren't moving. So that's why we can uniquely assign that peak to the OH bond. Now, if I move down my spectrum slightly, there comes a peak that matches the vibration of the carbon and the hydrogen. It's still a single bond, but obviously carbon has got a lower mass than oxygen, so a slightly different energy. What happens to our molecule when I get to that wave number? Well, now, of course, the CHs absorb that energy. The OH doesn't anymore because it's different. So now I've only got a response to the CH. So again, it's unique. We've identified it uniquely. So this is why in the region above 1500, I can uniquely assign peaks to bonds through the vibrations. Now, I mentioned the fingerprint region, and I mentioned that we can't always assign some of the peaks, which is frustrating because sometimes you do see a very sharp peak, but it's at a low wave number, so we don't actually see it on our table. But why is that? Certainly something is absorbing energy, but we can't uniquely assign it. Well, some of these modes are called skeletal vibrations. And here, as you can see, the whole molecule is vibrating. So although I see a peak in the fingerprint region, I can't identify it as unique CH, CO, CC, because you can see everything's vibrating. However, that peak is unique to this molecule. So if I were to change ethanol into propanol, for example, by inserting a CH2, that peak that requires to vibrate the whole molecule would shift. I'd get a different pattern. That is why the fingerprint region gives us a unique pattern for each molecule. And that's useful when you're using it as part of a database interrogation. Okay, so we've seen the infrared in action, we've run a liquid sample, we've seen our spectrum, and we've looked at some of the vibrational modes that cause those peaks to exist. It shows you how the energy is being absorbed. I mentioned at the beginning that we can also analyze solid samples as well. And the procedure is almost exactly the same. The only difference is that when we place the crystals on the sample stage, we have to compact them down so they have better coverage. I'm going to show you that shortly. Now, I mentioned it's a very versatile technique in forensics. We've looked at liquids, we've looked at solids. I'm now going to have a look at how the spectrometer can be used to run a solid unknown compound. Then we're going to use the database mode to rapidly identify the compound. And you see how quickly that can be done. And that's quite a common forensic technique. Then in the classroom, we usually go in and we say that an unknown white compound has been found in a student's locker and we need to analyze it rather rapidly. So this is the scenario. Now I'm going to show you how we can actually run that sample. So if we go back to our spectrometer, exactly the same as before, I'm using a very small amount of sample, but here it's crystalline. I've got my unknown white compound. I'm just placing a small spatula full of crystals on the same place, on that sample stage on the diamond. The only difference is that I now compact those crystals down so that they make better coverage on the crystal on the diamond. And as we zoom in, again, you can see our diamond crystal, and you can see I'm pouring the sample, so it covers it slightly, and they're stacked a bit like sugar lumps. You have to compact it down so that they fit or they give better coverage on the diamond. Once that is down, we run our sample in exactly the same way as we did with the liquid. So the only difference is that we put this kind of compression down onto the diamond. So now our unknown sample is on. We can go back to our laptop, measure the sample. I'm going to call it sample X because you don't know what it is at this stage. Run a sample measurement, and exactly the same way it's going to do 8 scans, just as we did before. It's then going to come up with our spectra for this crystalline compound. Obviously, this spectrum is quite busy. It would take a lot to pick apart, but I'm going to look at all those peaks. But then I use what's called a library search. So I'm just going to print out the spectra. Then I'm going to use the library search button, and the laptop will then take our spectrum, compare it with an online database, and as you can see already, it's made a match. it's identified a compound as acetyl salicylic acid, or simply aspirin, and at the bottom it's compared our spectra with its reference sample. It also shows a goodness of fit, so how confident is it that it's found the right spectrum. But you can see this was very useful. We took a very small amount of sample, we analysed it very quickly in only 8 scans, and we very rapidly identified it from its fingerprint region, as well as all of the other peak positions and the relative peak heights in the database to come up with the compound acetyl salicylic acid. So it's a very useful technique. Now, obviously, I'm sure you've been taught not to believe everything that comes to a computer. You've got to see, does that make common sense and chemical sense as well? Because obviously, if your compound isn't in the database, it won't pick it up. So you have to be sure. You also have to look at the spectrum. Are they overlaid? Does that make sense? And in this case, I'm confident that it is. And so our sample is indeed aspirin. So that shows you how we can use this infrared in a very rapid manner. I haven't destroyed that sample, so if I wanted to, I could take it off and either run another instrument using NMR, for example, or in forensics, that could be sealed up as evidence as well. I've not destroyed the sample. So that's another advantage of the infrared technique. Okay, so in the last kind of 50 minutes, I just want to go over some of the results. So it sort of ties together the theory, so you can see how you would use this information to analyze the samples. And I'm going to run through some of the samples that we had. First of all, we started with sample B, which was clearly an alcohol, because we saw this nice broad OH peak around 3,300, and we didn't observe any carbonyls around 1,700. So we only had the OH. This is actually the CH stretch. We didn't see any carbonyl. Now, sample H is also an alcohol. And so when we look at this part of the spectrum, you can see the OH peaks and the CH pretty much overlap because they're both OH functional groups. But when we look at the fingerprint region, we can see, yes, we have got completely different peak positions. That has changed. Now, these alcohols are very similar in structure. There's only a CH2 difference between them, but that's enough to give a very different fingerprint region, and that shows, again, backs up with the vibrational modes and also the database, how you can differentiate very similar molecules. So when we start looking at these samples, we have sample H. In the workshop, you're given an empirical formula, in this case, C2H6 and oxygen, so you know how many atoms you have. You're just going to work out how they're joined together. You have 3 pieces of information, that empirical formula. First thing you do is look at your mass spec that's given. Look for that molecular ion peak. Does the mass of this molecular ion match the mass of this empirical formula? If it does, then this is your molecular formula. If it doesn't, you need to ratio the mass of that formula until it matches your molecular ion. Once you've done that, you know exactly how many carbon, hydrogen, and oxygen are in your molecule. You then have to try and work out how they're arranged. For this particular case, we have sample H. We look at the infrared. There's clearly a nice broad OH peak. The CH peak is interesting from a spectroscopic point of view, but not very helpful to identify it because all organic compounds have CHs in them. So that's not particularly useful to us. What is useful is the absence of that CO stretch, C double bond O stretch. So the infrared leads us to believe possibly we have an alcohol here. When we look at the mass spec, this confirms as well when you look at the fragments. Well, actually with sample H, the fact that you only have 2 carbons, it doesn't matter which carbon that OH group goes on, it's going to be ethanol. So sample H was quite a straightforward sample to begin with. Well, when we look at sample B, the other one I compared, when you look at the infrared, it's very similar. In fact, apart from the fingerprint region, all we can tell from that is that we have an alcohol. When we look at the mass spec, we do have a different mass spec. We've got a different molecular ion because now we have 3 carbons in the backbone. The key here is to look at the next peak down, which is at 45, and the difference between the molecular ion and this peak is 15. That shows us that a lot of methyl groups are being fragmented from a molecule. So just looking at the infrared and the formula, we don't know whether it's propan-1-ol with the OH group at the terminal carbon, or if you put the OH group on the central carbon, get a propan-2-ol. But the mass spec shows that because we get a lot of methyl groups being produced, that would lean towards propan-2-ol. There are also some other fragments that you see that show that it must be propan-2-ol. So in this case, the mass spec helped us to identify the right structural isomer, which is propan-2-ol. Sample C that you'll see on the infrared, we now have lost this broad peak we had at 3,300. So sample C, although it contains hydrogen and oxygen, they can't be bound in an OH group. They've got to be bound some other way. But what we do see now is this sharp peak at 1,700. That is the carbonyl stretch. So this compound C certainly has a carbon double bond oxygen. And when we look at the mass spec, similar to the propan-2-ol, we see a large peak that's 15 different from the molecular ion. So again, a lot of methyl is being produced. And we also see a peak down here, which, well, I'll show you, confirms our isomer. So from the formula and the infrared, we could have either propanol or propanone. But the mass spec shows that actually with the loss of methyl and the fact that we see this fragment as well, it is propanone in our structural isomer. And in fact, if you could smell the solvent, it's a familiar smell, propanone. A common name for that is acetone, and acetone is a common solvent in nail polish remover. So that would have been a smell you might identify. So sample C was acetone, propanone. Sample D is interesting because it's now got a different infrared spectrum. We've got a more complicated molecule. We've got 9 carbons, 10 hydrogen. We now have 2 oxygens. So do they have the same environment, or are there 2 different environments for an oxygen? Well, when we look at the infrared, neither of those oxygens can be present as an OH group. We do see the strong peak again at 1,700. So one of them is definitely a carbonyl. But although it's in the fingerprint region, you do see a nice prominent peak around 1,300, 1,280. That is the carbon single bond oxygen. The reason there are 2 peaks is because although we have the same 2 atom masses, carbon and oxygen, the bond strength is different. Carbonyl, double bond, carbon single bond oxygen. So 2 slightly different energies, 2 peaks. A functional group that contains both a carbonyl and a carbon single bond oxygen is an ester. So this infrared has actually given us some indication that it might be an ester. When we look at the mass spec, there are some other clues. And in this particular case, we see a peak of the mass spec at 77. That is a very useful figure because it shows that you have this very stable 6-membered carbon ring, this aromatic ring, a benzene with a hydrogen missing. That is so stable that it survives the journey through the mass spec. So once you see that, you can draw that fragment, take 6 carbons, 5 hydrogens off your total and see what else it's joined onto. Another fragment here is a fragment of 45. That in the lookup table is an OCH2CH3 fragment. We know there's a carbonyl, so we can kind of join this together using all those different bits of information. Eventually we get this structure, which is ethyl benzoate and ester. And again, if you had the sample in front of you, you would smell that kind of ester smell as well. Well, the final sample, sample G, is a bit of red herring because if you use it, has a really nice smell of marzipan. It's a kind of almondy smell. And immediately you think, well, that's got to be some kind of ester. But it shows you've got to look at the evidence because our infrared, first of all, does show the presence of the carbonyl, but there's no peak for the carbon single bond oxygen. In fact, in the formula, we only have 1 oxygen, so it only contains a carbonyl. But our mass spec has this nice peak at 77. So when we put that information together, we come up with this structure. It is in fact benzaldehyde, which although not an ester, does have this characteristic almondy smell. So that is the sort of approach to compound identification that's useful for the A-level syllabus. When you do that, you really look at the unique peaks, so again, outside of the fingerprint region, apart from that carbon single bond oxygen. I showed you previously how you could look at the fingerprint region to pattern match. Both of them are used in industry and forensics as well, although commonly we use the database technique. So finally, I'm just going to finish off with a few examples of applications of spectroscopy. It's actually, as well as used in forensics, is used in law enforcement, for breathalyzing drivers to see if they've had a drink. They used to have to blow into a bag and you saw a chemical change. These days, it's a much more portable, more sensitive, more reliable, more accurate device, and it uses infrared. It's looking for a particular peak to look at the alcohol. That particular spectrometer you saw is also used to identify illegal substances. It is approved by the Home Office. So forensics and the Home Office do use the same equipment that we use to analyze compounds as well. It's also used in industry for quality control as well. Pharmaceutical industry, when you're manufacturing drugs, pharmaceuticals, to be honest, a white powder looks exactly the same, whether it's got impurities or not. So the infrared can actually look, it's a very sensitive technique to identify impurities, for example. Wine manufacturers as well, the infrared has also been used to identify particular compounds in wines as well. So there's a lot of application. And historical content as well. So obviously the art world doesn't want you to take its pictures, scrape some paint off and do some analysis. These are very valuable works of art. But because infrared is a non-destructive technique, you can analyze that painting without destroying it, without affecting it, and you can learn a lot about the pigments that's used. So again, for restoration and identification, it's useful for here. And Formula One actually uses infrared sensors in its engine cars to monitor the performance of the engine oil. Now, when engine oil degrades, the long chains break apart, and if anyone's seen oil from an oil change to a car, it goes in a nice kind of straw colour and comes out a very black, gunky sludge. But obviously, before it gets to that stage in a Formula One car, you've got a very high performance engine. Sometimes by eye it's not visible, so infrared is used to constantly monitor the infrared spectrum of the oil of the engine, so you can have real-time data of how that lubricant is performing in the engine. And in fact, this is something we took to the Big Bang Theory. We had our spectrometer at the Royal Society of Chemistry stand, and we gave people some lubricating oil, some antifreeze and some power steering fluid, and we tried to see, can you identify the compound as well? And just as before, we had a look at the spectra. For those that were doing GCSE, they could kind of pattern match. But for those that were doing A-level, you could then start to see, well, I can see evidence for an OH group, etc. here as well. So it's got a lot of uses as well. And in fact, this instrument is produced by Brooker. Up here in the Midlands, they have an office in Coventry. I'm walking down the corridor. It's interesting, they have some posters advertising the use for their spectrometer. I mentioned compound identification, quality control. Also, the food industry uses it. They want a consistent product, so it's used on the food production line. And I mentioned right at the beginning that you can analyze gaseous samples as well. And infrared is actually used to monitor air quality as well. It's very sensitive. There are molecules in the atmosphere that are infrared active, such as carbon dioxide, water, oxides, and nitrogen, for example. So a lot of industrial applications. And finally, just as I come to the final part of the stage, it's actually used in research as well. So I have a colleague, Dr. Sarah Horswell, and she is interested in catalytic converters and the chemistry that occurs on the catalytic surface. Now, even with the largest, most highest resolution microscope, you can't see individual gaseous molecules docking with the catalytic site, but you can identify their alignment and other characteristics by looking at their infrared signature. So she uses infrared to look at the alignment, the docking, and the concentration of catalysis as well. So infrared is a very useful technique. Yes, you have to learn about it at A-level, and hopefully when things get back to normal, you'll be able to use one of these instruments yourselves. But also it's used in industry. It's used commonly in forensics, as I mentioned, because now you can appreciate how rapid, how sensitive, and how versatile this particular instrument is for industry as well. So I believe my time is up. Thank you very much for your attention. Hopefully that's made your syllabus a little bit more interesting, shown you some of the techniques that are used, and hopefully given you a wider perspective. I will make all this information available for you to share and download afterwards. Thank you very much, and I now hand over, and I'm very happy to answer any questions that you may have. So thank you very much.
Okay, thank you very much for listening. That was a very interesting talk by Dr. Reed. I mean, I especially realized how versatile and the variety of uses that Infra-Red really has. So I guess we'll move on to a few questions.
Yeah, the first question is by David Hu, and he's asking, hi, is the sample for infrared spectroscopy in solution or in pure liquid? If in solution, wouldn't it measure also OH bonds in water?
That's a very good point. Yes, absolutely right. If you were to dissolve something in water, your sample would be swamped by those OH peaks. So the sample does have to be pure. And so the liquids I used were pure liquids. The solids were run as a solid, they weren't dissolved. But that's a very good point, because if you're looking at drugs, for example, quite often they're not pure substances, and you'll see many other peaks. So there you can't assume it's a particular pure compound. That you have to rely on data manipulation and the database and the software to almost unravel those peaks and to sort of see what is there. But that is quite complicated. So yes, that is one point. The compound to identify does have to be in the pure form.
Okay, I hope that his question was answered. And we go to the next question by Louis Goodwin. And he asks, how often is IR spectroscopy actually used in forensics? And he mentioned that he'd written an essay on WADA and performance enhancing drugs, where he found out that they mainly used a combination of chromatography and mass spectrometry. So
No, that's very true. So as I mentioned, it's rare that we would use just one technique. So yes, chromatography, NMR are very powerful techniques, and they are used in conjunction with infrared as well. Infrared is used quite routinely just because it's very simple, and because it doesn't destroy a sample, it gives you some information straight off. What you would then do following the infrared, take that sample and then say maybe perform NMR or chromatography with it. It depends on the particular drug you're looking for, the particular application, but it is used. As I say, it's not the main technique, but it is one of the techniques, and certainly because of its sensitivity and the fact that it doesn't distort the sample, it is used a fair amount.
Alexandra Galoni asks, is every bond IR active, i.e. would every bond absorb energy?
That's a very good question. Typically, the energy ranges that we see within the infrared region are, if we like, for organic compounds, so CHCO, etc. If I were to put salt on there, which is obviously sodium chloride, the ions are a similar distance apart, but their energy is much different because we've now got coulombic interaction and ionic bonding rather than covalent bonding. So that energy would be much higher and actually outside of the infrared regime. So this is where infrared really lends itself to organic compound identification. So in organics, for example, it's not that useful. So yeah, the energy range of that vibrational mode has to sit within the infrared region. But yeah, very good question.
So our next question is from Jeremy Cohen, and they ask, is it IR spectroscopy machines that are used in airport security when they swab clothes or a suitcase?
Yeah, again, that's a very good point as well, because again, they're looking for explosives, narcotics. Explosives, again, are organic compounds. And as I mentioned, for the reason that it's a very sensitive technique, they take a swab, they swab your clothes, they're not putting solvents on you. That is then used for infrared. It's not destroying the sample, so if they do pick something up, they've not destroyed it, they can do further analysis. They also use GC or gas chromatography and mass spec as well. So it's a combination of instruments, but infrared is certainly one that's used by the airport security as well. So yeah, next time you're swabbed and it goes into machine, you now know the technology it's being used and what it's looking for.
I guess a question that I have myself is what actually causes the like the bonds to vibrate? Is that just like what they do, or can it be explained?
Yeah, so unless you're at 0 Kelvin or absolute zero, everything is moving, everything is vibrating, it's got an energy to it. And once you have that energy, that thermal energy, these bonds will vibrate in a certain manner. So yeah, anything that's above 0 Kelvin will be moving, will be vibrating. When you irradiate with the infrared, you are giving it more energy, so you're exciting that bond, you're heating it up a little bit, so it'll vibrate more, for example. But yeah, everything above 0 will vibrate, will be moving. Obviously, if you get too hot, it's going to dissociate, but while it's joined together, yeah, you'll get a signal.
So I had another one of my own questions. So is IR useful for, say, differentiating between geometries of, say, the same molecule? Because I know that some drugs could have different impacts based on the different, say, optical isomers that they could have.
That's a very good question, and you're absolutely right. In chemistry, an optical isomer may have a very different response in the body. Unfortunately, infrared isn't too good at that. Infrared will tell you what bonds are there, but it won't tell you how they're joined together or what the geometry is. So that's when you have to look at something like mass spec that looks at the fragments, or when you get to year 13, you'll look at NMR that tells you the environments adjacent to carbon atoms. So infrared, for that purpose, unfortunately, isn't very useful. It tells us what's there, but no, it doesn't give us much information about the geometry. We do have to use other techniques.
So Ava Patel asked that, like, how long is the overall procedure when you have to compare your results? And is it possible that one technique could perhaps show a strange anomaly when another seems to be, well, all the others seem to be correlated?
Yeah, that does happen in sort of real life when you're analyzing compounds. Sometimes you do get a result that doesn't compare. So you have to look at the balance of evidence from all the other systems and make a judgment about that. In terms of timing, as you saw the screen, once your intercept is set up, and it takes maybe 10-15 minutes to set it up, there's no sample preparation. You put your sample straight on. In real time, within seconds, you get the trace. If you've got a good database to compare with, again, that's just seconds to make a comparison. If not, and you're trying to identify it yourself, it's just a time for you to look at those peaks. But if you're using an automated system, literally it's minutes and seconds to get results in this technique.
So our next question is from Edward Starr, and they ask, could there be different energy readings at different temperatures for the bond? So would it give different results, or can the IR machine compensate for that?
That's a very good question. One thing you might see on more sensitive techniques is the kind of peaks broadening or changing shape slightly, but they'll always be at the same position, the same peak. But typically, because this is a bench instrument, you run it at ambient temperature. Typically, your sample is is at room temperature. If it were too hot, for example, you'd have problems with it evaporating off the surface. Too cold and it might freeze and be a solid. So typically we run our samples at room temperature for that reason. So we're looking at peak shapes. And if they were too hot, you might see some effects like peak broadening, but in general, the procedure is to keep your sample at room temperature.
And Alexandra Galoni asks, can you talk a bit more about the different types of stretching and bending? Do they all have different energies? And this is for the same bond?
They do have, so if you're stretching a bond, imagine two masses with a spring in between, and from physics, you're looking at sort of vibrational modes. The energy to stretch the bond, as I mentioned, is a function of the mass of the two atoms and also the strength of the spring between them. You can imagine a double bond having a stiffer spring. That's the standard bond stretching. But there are other ways that the molecule can absorb the infrared and have a mode. I showed something called wagging, which is where the molecule just moves from side to side. There's a bending motion where the bond doesn't increase or decrease its distance, but it increases and decreases its angle between. So there are quite a few different ways that the atoms can respond to the infrared, and each of those has a slightly different energy requirement as well.
So our next question is from Oliver French, and he asks, why are some peaks so broad, but others are so thin?
That's an excellent question and well observed. So if we look at the peaks that I showed in this seminar, we saw that the carbonyl at 1700 was a very sharp peak, but we saw the OH peak for an alcohol about 3300, which is very broad. One reason for this is that there are many modes, such as the bending, the stretching, but I think one of the common reasons is the fact that for OH, for example, in your solution, you have hydrogen bonding occurring. So those OH groups are forming a network of OH bonds around them. Each time you have a hydrogen bond with another OH group, you're slightly affecting the energy of that OH bond. Because you're slightly affecting it, you'll have a distribution of energies. So you'll have a distribution of wave numbers and hence a broader distribution of peak. So sometimes the broadening is a measure of hydrogen bonding. But that's a very good observation, yeah.
And I guess another kind of question that I have is that, you know how they have different ways of vibrating and stuff in the molecule. What makes one way of vibrating have more energy than the other? Is it just the geometry of the molecule?
Yeah, it's just an energy penalty. For example, if you have two atoms joined together for a particular infrared wavelength, there might not be enough energy to stretch that spring apart, but there could be sufficient energy just to bend it or just to move it a little bit. So it really depends on what energy is available, what the molecule does. If it doesn't have much energy, it might just do a bending mode. If it has more energy, it will actually stretch the bonds. Yeah.
Okay, so I just want to thank you very much for the really interesting presentation and answering all of our questions. And yeah, I just want to remind everyone that these Thinking About talks happen every Tuesday at 4 p.m. And I hope you can join us next week where we'll be thinking about linguistics. Yeah.